Let's look at derivative of exponentials and logarithms. So what if I wanted to know what the derivative of e to the x was? And I could use my derivative definition, which says where you see an x, plug in x plus h. Where you see an x, plug in an x. Then what I could do is kind of work backwards. Some of you know when you have the same base, what do you do with the exponents? You add them. Well, I could split them. If they're being added, I could write e to the x times e to the h. And then what I could do is I could factor out an e to the x up top. So that left me with an e to the h minus 1. And then I could bring the e to the x out front because that's a constant. It has nothing to do with h, so who cares what h is? So only this piece right here is our problem. And your book gives this definition that this piece equals 1. But if you want to know why, you could put very small values of h, like 0.0001, and you would see that this piece, as the limit as h approaches 0, is going to 1. And thus, if this piece, this limit is 1, then the derivative, because this is the definition of a derivative of e to the x, is just e to the x, which is kind of cool, right? So that's an easy one. Let's look at a couple of examples that involve finding the derivative of e to the x. We just said the derivative of e to the x is e to the x. What I would do right now is I would pause this video and I would answer each one of these and then come back and see if you got the correct answer. So if you pause the video, welcome back. Let's look at this very first one. So this 5 is just a constant that goes out front, so we're still just finding the derivative of e to the x. So that would stay 5 times e to the x. This, of course, is our power rule, so 4 times 3 gives me my 12, and I subtract 1 from the exponent. And then this is my linear piece, so the derivative of 9x would just be 9, and then the derivative of this constant would be 0. Now let's look at example 2. This first derivative, don't let it throw you. This isn't e to the x. This is x raised to e, which e is a number, remember? E's that 2.71828 number. So I would do the same thing as a power rule. I would bring this e down and then I would subtract 1. Then my 2e to the x would become 2e to the x. And e to the second power is a constant because e, again, is a number. So that would just simply be, this piece would be a constant, and the derivative of a constant would be 0. All right, the last one here, if I find the derivative of e to the 5x, there's a nice little formula that says this derivative here, when you take the derivative of e to the kt, okay, where k is the number comes down, okay, off that variable, and then we leave this piece the same. There'll be more about this later when we talk about the chain rule. Let's look at what is a logarithm. I always, find it, students will always come up to me and say, I did okay in algebra, but I never really understood logarithms. All a logarithm is an exponent. All a logarithm is an exponent. It's just a way to display a number that's very, very large or very, very small. But if you can remember, a logarithm is an exponent, then you got it made. Where these are your bases. So notice, with exponentials, you have base to a power. Well, a logarithm, you have a base of a value equals the power. There's many different properties of logs, and if you get down the properties of exponential, it's kind of cool because they're the same. If you remember with an exponential, if the bases are the same, you add the exponents. Well, look at there. A logarithm you can split up. If you're multiplying, you can split up by adding. Dividing, remember if you're dividing exponents with the same base, you subtract the exponents. Well, guess what? You subtract the logs. This one's kind of nice that you can bring this power down out front. and then this ln, now notice these are my natural log of a equals x if and only if e, because ln is base e, to the power, okay, a logarithm is a power, an exponent equals that value, ln of 1 equals 0, ln of e equals 1. The reason why is how can I get 1 e raised to the 0 power? How can I get e raised to the first power? Ln of e to the x, these kind of cancel and you get your x, and then the same for the inverse, e to the ln of x. And I mention inverse because that's what's so nice, is that these are inverses of each other, exponentials and logarithms, because this way it makes it very helpful to only know one set of properties. So the natural logarithm is our base e logarithm. So in other words, this is our e to the x, because that's our base, and this is equivalent to the natural log, okay, the natural log of y equals my exponent. Now, if you're interested, if you're a math nerd and you want to know the y, you can certainly go through the derivation in the textbook of this derivative, but I'm just going to tell you the derivative of ln of x is 1 over x. So you should have that written down on your formula sheet, ready to go. When I say find the derivative of ln of x, you got 1 over x. So let's look through a couple of examples. Again, I would hit pause and I would try to do these on your own. Welcome back. Let's see how you did. So if I want to find this derivative, well, we just said the derivative of e to the x is e to the x. The derivative of ln of x is 1 over x, but I have this 5 here, so that piece goes up top. Then down here, I have a power 4x cubed. Here, notice that log rule says I could bring that 4 out front, so this becomes 4 ln of x, which would be 4 times 1 over x, or simply 4 over x. There are some other type of functions that you might encounter, this a to the x, where the a would be like a number and the x is your variable. The derivative of this is you repeat it and then ln of a. So for example, if I had find the derivative of 2 to the x, I would get 2 to the x ln of 2. And you see this a lot when we get into some of the banking and compound interest. So write this one down, because students seem to forget about this one when we get going doing other derivatives. This is a very important one. And then we also have the derivative of log base anything, base a, equals 1 over ln of a times 1 over what's inside here, the parentheses. So if I had the log base 4 of x, this would equal this format, 1 over ln of 4 times 1 over x, and of course I could put these together. So let's see some other examples. Again, you might want to pause so you could do these on your own. If you paused, welcome back. So here's the a to the x, so I would just simply get my little formula and say I repeat that, ln of the base, minus repeat 3 to the x, ln of the base. This one down here, what I did is I split this up, so in other words, notice that I could either say, probably the easiest thing to do is bring that 5 down front, and so then this piece right here would become 1 over ln of 4, and then that, of course, this piece right here would become 1 over x to the 5th. Now notice this piece right here, I'm actually having to take the derivative of x to the 5th as well. So that's where I'm getting this 5x to the 4th, where things cancel. If you would have done this, let me just get me a little writing pen here. If you would have started with this, because this is kind of getting into a future lesson called the chain rule. So probably the easiest thing to do would be to use your log rule, and I can bring a constant out front. So I could bring that 5 out front and then get my log 4 of x. The 5 is still out front. This definition we said was 1 over ln of the base times 1 over x. Well, if you put it all together, that's that piece back again. So it just might be a different way to see how this one's written out. So an internet store sells Australian wool blankets. I don't know what Australian wool blankets that difference makes, but there you have it. If the store sells X blankets, so X is the number of blankets, at a price of P dollars per blanket, then you are given a price demand equation. I can already see, because this is just a constant, that this is my a to the x part. So the first part is recognizing what type of a function this is. Find the rate of change. Hey, that's a derivative. Rate of change of price, okay, with the respect to demand, change in price over change in demand, when the demand is 800 blankets, and then interpret. So first of all, we need to find the derivative, and then we'll plug in the 800. So again, up here, I recognize that this piece looks just like A, where my A is 0.999999. Did I say enough nines there? Yes. The 350, this piece right here actually could just come out front, because that is just simply a constant. And so the 350 comes out front. I take this derivative, which is the 0.999 to the x times ln of 0.999. And now to find for 800 blankets, I plug in 800. I get my nice little calculator out, and I can put this in my calculator, and I get this 16 cents. So put this in your calculator. Don't just stare at this and say, looks good, Cindy. Make sure you can get this value and tell me what it means. Well, it looks like when the demand is 800 blankets, the price is decreasing. So you might say, well, how did you go from a negative to positive? As long as in my interpretation, it probably would have been better to leave that as a negative, I'll be honest with you. But as long as my interpretation is that this is decreasing, that tells me it's negative. So when the demand is 800 blankets, the price is decreasing by 16 cents per blanket. Let's look at another example of this systolic blood pressure and age. So this P of X is my function. So this is my model that relates this systolic blood pressure and age, where this is the pressure measured in millimeters of mercury, and X, so it's a function of the age. And this function is only from 0 to 65 years old. Find the rate of change, derivative. When you see find the rate of the change, that means to find the derivative, and then figure out the rate of change of the pressure. Okay, so in other words, the change in pressure with respect to age of 10, 30, and 60 years. So how did I so quickly find that derivative? Because you got these down, right? The derivative of 40 is a constant. Bam, went away. This 25 is just hanging out there out front. The derivative of ln of something in parentheses is 1 over that something in parentheses. So that's how I got the derivative, and now I'm going to plug in my 10, 30, and 60, and I get my 2.7 millimeters of mercury per year. Okay, my change in my pressure over the change in the year. And of course I can even look at this at a graph to see, in this case, to see that certainly this is going up as age goes up, which would be expected.